In this video, we are going to continue our investigation into trigonometric integrals by specifically concentrating on the case with tangent to a power, secant to a power. So as a reminder, in the previous video we discussed sine to a power, cosine to a power, and saw that it worked out very nicely. If one of the powers is odd, you have a technique you could use, and if both of them are even, you have a separate technique. We're going to see a similar approach for tangent to a power, secant to a power. Once again, you need to make sure that you know your Pythagorean identities, and your half angle identities are once again useful with those even powers of sine and cosine. In terms of evaluating tangent to a power, secant to a power, the methods used are outlined here. I will let you read through them, where I've included them purely for the sake of completeness. Now what we're going to do is investigate 3 examples that illustrate kind of parts 1, 2, and 3 in that exact order, so we'll see exactly how we can use these techniques. So for this first example, tangent squared, secant to the 4th. Note the power of secant is even, so we're going to use the techniques outlined in case 1. So what we are going to do is save a secant squared to play the role of du, and rewrite the remaining secant squared in terms of tangent squared. So this becomes the integral of tangent squared of 2x. And for now, don't worry about the fact that there's a 2x. We will hopefully see that we can very easily handle that as part of our approach. And then we're going to write secant to the 4th as secant squared times secant squared. And the idea is going to be to rewrite this remaining secant squared in terms of tangents so that the secant squared 2x dx can play the role of our du. So using our Pythagorean identities, which once again are very useful for us to remember, secant squared is 1 plus tangent squared. So here remember it's 2x. And now we are in an ideal situation to apply a u substitution. So we're going to let u be equal to tangent of 2x. Then using the chain rule, du is going to be equal to what? Secant squared 2x times 2. So 2 secant squared 2x dx. So this secant squared that we've saved becomes 1/2 du. So putting this solely in terms of u, as we saw in this previous case with powers of cosine and sine, we'll have a 1/2 that pulls out front. Then it will become u squared 1 plus u squared du. So it almost works out too good to be true. Rewriting in that proper way, doing a substitution, what we are left with is an integral only involving powers of u. So go ahead and expand out. We'll have u squared plus u to the 4th, both functions that we can easily anti-differentiate. So the 1/2 is hanging around out front. We have 1/3 u cubed plus 1/5 u to the 5th plus c. And our last step is to simply resubstitute each u is equal to tangent of 2x. So distributing the 1/2 at the same time, we have 1/6 tangent cubed of 2x plus 1/10 tangent to the 5th power 2x plus c. So to recap the method that we've used, if the power of secant is even, save 2 of them to play the role of du. The remaining even power of secant can be rewritten via the Pythagorean identity to get in terms of tangents so that you can do a substitution. Now we are going to take a very similar approach to evaluate the integral of tangent cubed times secant to the 5th. And in this case, the observation is going to be that the power of tangent is odd. Whenever the power of tangent is odd and there are tangents and secants present, what we are going to do is the following. We are going to take one of our powers of tangent. So we have tangent squared And I'm also going to take one of my powers of the secant. So I'm going to write this as secant to the fourth. And then what remains is a power of the secant and one of the tangents. And the reason we have done this is now combined together, the secant tangent is going to end up playing the role of our du. And in order for that to be our du, u is going to have to be secant, which means that the tangent squared needs to be rewritten in terms of secant. So this becomes the integral of, and tangent squared is secant squared minus 1. And then cutting and pasting the rest down. Secant to the fourth times secant tangent. So we're kind of very similar here in terms of the overall approach. Because the power of tangent is odd, and we have some secants. What we do is we take one of the tangents, one of the secants, we save those to be our du, and we take whatever the leftover even power of tangent is, and we rewrite it with the Pythagorean identity. Now that we've done so, we can do a substitution. So u equals secant x would give us that du is secant tangent. So our integral very conveniently, once again, becomes u squared minus 1 times u to the fourth du, which is once again the ideal situation. Take the u to the fourth, distribute it through. When you do so, we're left solely with powers of u, which we can very easily anti-differentiate. So individually here, 1/7 u to the 7th minus 1/5 u to the 5th, and then we resubstitute so that each u becomes a secant. So 1/7 secant to the 7th power minus 1/5 secant to the 7th power plus c. And the technique that we've used in this example corresponds to method 2 given in the second slide. Also, let me note that in order to use this technique, all we need is for this tangent power to be odd. So it just as easily could have been tangent to the first or tangent to the 11th. The last example that we wanted to cover in this section was something that corresponds to the third technique. So let's go ahead and evaluate the integral of cotangent to the fourth. So if it's cotangent to a power and cosecant to a power, the same techniques apply as they would with tangent and secant. So what we are going to do, because it's just a cotangent to the fourth power, is we are going to rewrite using the Pythagorean identity by breaking it up. So we're going to write this as cotangent squared times cotangent squared. Now, if we had started off with cotangent to the 6th power, we would have 4th power and 2nd power. And then what we're going to do is take this cotangent of squared that we've pulled off and rewrite it in terms of cosecants. So recall from our Pythagorean identity that cotangent squared is equal to cosecant squared minus 1. And now that we've rewritten the cotangent squared in terms of the Pythagorean identity, we are going to take our leftover power of cotangent and expand it through. So this becomes the integral of cotangent squared times cosecant squared. I'm going to break it up into two integrals, minus the integral of cotangent squared. And now that we've broken it up into two integrals, we can evaluate each of the integrals individually. So let's just begin with the first one. And the observation I want to make here is that I know the derivative of cotangent is minus cosecant squared. So for that first integral, we're going to use a substitution. We are going to let u be equal to cotangent of x, so that du is minus cosecant squared. With this observation, the cotangent squared becomes u squared, and cosecant squared is the opposite of du. So the first integral is going to turn into minus the integral of u squared du, which is minus 1/3 u cubed, and u is equal to cotangent. So minus 1/3 cotangent cubed of x. But of course we have this second integral that we also have to take care of. And what we're going to do is kind of just continue on with the process we started with. If it's just a power of 2, so an even power, no secants around, we are going to rewrite in terms of the Pythagorean identity. So just use that same technique we've already used. Cotangent squared is cosecant squared minus 1. And individually, we actually know the antiderivative of cosecant squared, and we know the antiderivative of 1. The antiderivative of cosecant squared, looking above here, is minus cotangent. But if we distribute through the minus sign, that would become minus a minus cotangent. And the antiderivative of a positive 1, so we're going to distribute that minus through, is plus x. And then we simply carry this down one more step so we get a nice looking solution. And to recap this method, if the power of cotangent or tangent is even and you don't have any secant or respective cosecant term, what you do is you take one of those even power and you rewrite in terms of the Pythagorean identity. And if you need to continue on and use that same technique, you do so.